Let's get started with lecture 12. So last time we talked mainly about vertical oscillations, and basically what we found was that if you attach a mass to a vertical spring, well, the only thing that happens, the only thing that's different from a horizontal spring is that the equilibrium position gets shifted down by a length L, and then if you balance out the forces, Lk is equal to mg. So L is, for example, mg over k. And then the rest is the same as the case of horizontal oscillations. So you just have this new equilibrium position, and then depending on your initial condition, you have an amplitude. So you oscillate, let's say, with some amplitude A around this equilibrium position. And we have the same equation. So there was not much of a difference ultimately between the two scenarios. Another classic example of simple harmonic motion is a pendulum with a small angle. A pendulum with arbitrary angle is a bit more complicated. So suppose you hang a mass from a string and then you move it away from this vertical equilibrium position by some angle, and then you let it go, and then it's going to do something like this. So it performs circular motion around this finite arc, goes back and forth around the equilibrium position. And in general, for a large angle, this is not a simple harmonic motion, but it turns out if our angles are small, so we're kind of close to the equilibrium position, so something like this, so you just have some small oscillations around this, then we can describe this motion by a simple harmonic oscillator. It is generally true, I think it's worth it to mention it at this point, that any system that has a stable equilibrium position, if you oscillate, around it by some small amounts, small distances, then you can describe the motion by simple harmonic motion. The easiest way to understand it is to think about the potential energy. So let's say you have some arbitrary potential energy, U of x, let's say, and let's say that's x. Right, so everywhere you are, there's some potential energy. Okay, so the stable equilibrium position is where the potential energy is minimum. Right, so the forces have to be zero if it's in equilibrium. That means that the derivative of the potential with respect to position is zero. Remember, force was I think minus the derivative of the potential, depending on how you think about the sign. So then, yeah, so if the force is zero, all these places where the force is zero are equilibrium positions, but the minima are stable equilibrium. So you can think about it as like one example is think of the potential as a frictionless surface. So gravitational potential is just proportional to the height. So if you put an object here, yeah, it's going to stay there, but if you push it a little bit this way, it will slide down. So that's not stable. There's an instability there. However, around the minimum, yeah, you push it a little bit this way, it comes back, and what it does, it's going to oscillate around that equilibrium position. So the idea is that to a good approximation, if you're very close to this minimum, so let's just focus around the minimum. we can approximate our potential for those small distances with a quadratic curve. So let's say that's the general potential. Here you have the minimum. So you know the minimum is, at the minimum the derivative is 0. And if we match the second derivative, we're going to get some quadratic curve that has the same value at this point, the first derivative, the same first derivative at this point, and the same second derivative at that point. So first derivative is 0. For those of you who've heard about the Taylor expansion in calculus, this is just a side note, some of you may not have heard about this. Any function we can expand around any point. So let's say that's some point x0. We can write u of x is approximately u of x0. That's if the derivative is 0. If you want to keep the first order corrections, you would keep the first derivative and then the second derivative over 2 factorial x minus x0 squared, and then you can keep more terms. So every term you keep, you keep a polynomial that has derivatives matching. So if you keep up to this term, first and second derivatives match. If you keep another term, also the third derivative matches. And the more terms you keep, the better your approximation becomes, etc. So we know that at the minimum, this term is 0, right? 0 at minimum. The derivative must vanish. And then we're just going to get some constant plus constants in the potential energy never matter. As we said, it's always the difference of the potential. And then it really looks like a spring, right? This is the displacement from the equilibrium position. The equilibrium position was at x0. So you have distance from the equilibrium position squared times a number, right? So if your spring constant is this second derivative of u at the equilibrium position, it really behaves, making that approximation, neglecting higher order terms, like a spring. So that's a very generic statement. Okay, so let's now focus on the pendulum. And let's think about, this is our pendulum here. That's the equilibrium position, let's say at some position away from equilibrium, so at some angle theta. Okay, so how do I think about, let's say, the potential energy of this? Well, if the potential energy, for example, is 0 here, I'm interested in this height, right, from here to here. And let's say the length of the pendulum is L, so from here to here I have L, from here to here I have L cosine theta, right? That's adjacent to cosine theta in a right triangle whose hypotenuse is L. So this length here is L minus L cosine theta, which is, I can factor out the L, 1 minus cosine theta. So you can always write u of theta as mg L 1 minus cosine theta. The minimum is at theta equals 0, right? As you can see, it's here. And we see that the derivative vanishes because the derivative of cosine is minus sine, and sine of 0 is 0. All right, so now if I want to approximate this by a polynomial, well, let's think about cosine of theta is approximately cosine of 0 plus the derivative of the cosine, which is minus sine at 0, times theta, right? I'm using this formula, so this is matching the first derivative. and then the derivative of minus sine, which is the first derivative, is minus cosine again. So that's minus cosine 0 divided by 2 factorial times theta squared. Okay, so if we make that approximation, we find that cosine of 0 is 1, sine of 0 is 0, as we expect, because that's the equilibrium position. The first derivative must vanish. Cosine of 0 is again 1, so that becomes minus theta squared over 2. That's for small theta, if I'm allowed to neglect higher order terms, that's a good approximation. So now for small theta, I can write u of theta is approximately mgl times 1 minus 1 minus theta squared over 2. So that becomes 1/2 mgl theta squared. Okay. So we then kind of expect a harmonic oscillator. And let's see, so what is the kinetic energy? Well, the kinetic energy is 1/2 mv squared. And if it's going around the circle, v is r omega. Omega is the derivative of theta with respect to time. So this is going to be 1/2 m r squared d theta dt quantity squared. So it's helpful to kind of compare this with maybe a mass on a spring. So mass on a spring k was 1/2 m, velocity, which is dx dt squared, and u was 1/2 small k, the spring constant, x squared. So the kinetic energy is something times the derivative squared. The potential energy is again some number times x itself squared. So you can see there's some mapping right here. The potential energy is something times theta squared, and the kinetic energy is some number times the derivative of theta squared. So we can already guess the period of this harmonic motion using a mapping. So remember here we had omega was square root k over m. Right? Now, so it's really the square root of the thing in front of u divided by the thing in front of k, if you wish. So our guess here would be that omega for a pendulum should be the square root of the thing in front of theta squared, which is mgl. Let me change this r to l, right? The radius is, of course, l, right? So sorry about that. The radius of that circle is the length of the string, which is l. So we're going to get mgl over ml squared, and this is square root g over l. Okay, so we can also make sense of this, again, using the small angle approximation, if you think about the forces and accelerations of this this particle or this mass that's attached to the string in the pendulum. So again, let's go here at some angle theta, and we can think about the free body diagram of this mass. So there's going to be the tension force and there's going to be its mass. Those are the only forces. So I can decompose the mass in the radial direction. So let's do that here. Say that's T. And if you decompose mg, we're going to get mg sine theta in this direction and mg cosine theta in this other direction. So mg sine theta is what's going to give us kind of this angular acceleration. It's going to change d theta dt, if you wish, right? So the acceleration in this direction here will be L second derivative of theta with respect to time, right? This L times alpha is the acceleration that way. And mass times that must be the force, net force in this direction, in the tangential direction. So that's mg sine theta. Again, we can make the small angle approximation. So if theta is small, probably remember this from the previous courses, there was this geometric understanding of it that if you take a unit circle, this vertical is sine theta, and this little arc is theta itself in radians. And as you make theta smaller and smaller, geometrically these lengths get closer and closer. We can also think about it in terms of Taylor expansion, right? So we can say sine of theta is sine of 0 plus the derivative of the sine function, which is cosine function, right? The derivative of sine theta with respect to theta is cosine theta, and then we put the value of 0 times theta. So this is 0, this is 1. So, and let's say we keep it to first order, we don't go to higher orders. So this is approximately equal to theta, thinking about this expansion in terms of derivatives. All right, so then the equation we get is the second derivative of theta with respect to time squared. M's cancel out, that's g over L times theta. And let me be a little bit careful with the signs here. So the acceleration is minus that, right? Because it's moving this way, right? But theta increases in the opposite direction. So if we're careful about the signs, there is that minus sign in our equation, right? As theta was defined going this way, counterclockwise, and the force we wrote was this way. So that gives us a minus sign, let's say, here, if we take the sine of theta into account. So now we see that's basically the same governing equation, right? The acceleration is something times the displacement itself. Remember, x of t was in general a cosine omega t plus some phi naught, and velocity therefore was minus a omega sine, and acceleration was minus a omega squared cosine omega t plus phi naught, which is minus omega squared x of t. So whenever you have an equation of motion where the second derivative with respect to time of some quantity, here the acceleration, which is the second derivative of position with respect to time, is equal to a negative number times that quantity itself, then this thing is omega squared. Omega, therefore, is the square root of that coefficient. So two different ways we saw that the angular frequency of a pendulum for small oscillations, if we can make the small angle approximation, is just the square root of g over. Okay, so let's practice a little bit with this thing that we derived. So it says a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. If the ball is replaced with another ball having twice the mass, the period will be what? So think for a few seconds and we come back. Okay, so yeah, so we just found the period. It was the square root of g over L. It doesn't depend on mass, right? Because because the force is proportional to the mass. So in the F equal ma equation, the mass just cancels out. And it shouldn't change. What about this one? So we're saying on planet X, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. Now, if you take the pendulum to the moon of planet X, where the free fall acceleration g is half as big, the period will be what? So it's yeah, think for a few seconds about this. Okay, so we said omega is the square root of g over L. What was omega? It was 2 pi over t, right? So t is going to be proportional to 1 over square root of g, right? Now, let's do this a little bit more slowly. So we said omega is square root of g over L for a pendulum. Therefore, 2 pi over t is omega. And t becomes 2 pi square root L over g. So let's say if g goes to g over 2, what happens? So let's say t1 is this. 2 pi. So what happens if g is reduced by a factor of 2? So what happens if g goes to g over 2? Well, t1, the period on planet X, is 2 pi square root L over g. t2, the period on the moon of planet X, is 2 pi square root L over g over 2, which this 2 goes upstairs, so that's 2 pi square root 2L over g, which is square root 2 times the same thing, 2 pi square root L over g. So it gets larger by a factor of a square root 2, right? It's proportional to 1 over square root g, so if you cut g by half, you make it larger by a factor of a square root 2. Okay, going back to our example, square root 2 is roughly 1.4, so that multiplying 2 should give us 2.8 seconds. Okay. So again, this is kind of the general strategy. So we've looked at two systems, right? We looked at the pendulum, we looked at the mass on a spring, and basically that's the general strategy. If you have a more arbitrary system, more complicated system, as long as we can identify a quantity whose second derivative with respect to time is minus some positive thing times the quantity itself as a function of time, we know that we have simple harmonic motion, and the angular frequency is given by the square root of that. So this will become helpful in finding the period, let's say, or the angular frequency or the frequency of more complicated systems that exhibit simple harmonic motion. Using their description. Another way, which we also talked for the pendulum, is to think about the energy. If you can also approximate the potential energy as something times this dynamical variable squared, and then the kinetic energy is something else times the derivative, the first derivative with respect to time, of that dynamical variable quantity squared, then again the ratio of these coefficients can be used to find the angular frequency. All right, so we'll do some examples to get more practice with this. All right, so let's do a couple of examples here. Just finding the finding the period or the frequency for a given system. So let's say, what is the angular frequency? So the first system is something like this. So suppose you have a mass m that is sandwiched between two springs. So one is here with spring constant k1, another one is here with spring constant k2. Okay, so so we want to find, let's say, the frequency, the angular frequency of the oscillations as a function of m, k1, and k2. So how should we do it? Well, we can again say there's going to be some equilibrium position right here. There is no force on it. And then we can imagine moving, let's say, a distance x to the right, for example. So let's consider these distances with a sign. Okay, so I put a coordinate system whose origin is at the equilibrium position. So if it moves here to x, so moves to the right, x is positive, let's say. What happens is k1 is stretched, so more than whatever it is, right? So initially, I mean, the equilibrium position doesn't have to be the natural length for both of them. As long as the forces they exert cancel out, it's in equilibrium. But if it moves a distance x this way from the equilibrium position, well, there's going to be an additional force this way from that spring, and that's k1x. And now k2 gets compressed, so it will exert a force this way, k2x. Right, so from this free body diagram, we have a net force k1x plus k2x to the left. So the net force, if I think about the positive direction being to the right, is minus k1x minus k2x. So that's, let's say, sum fx. And that's minus k1 plus k2 times x. And this is equal ma, which is mass times the second derivative of position with respect to time. So then I can write, if I divide by by mass, the second derivative of x with respect to time for this system is minus k1 plus k2 over m times x. And then we figured out that whenever you have the acceleration or the second derivative with respect to time is some negative number times the dynamical variable itself, this coefficient is omega squared. So omega becomes the square root of k1 plus k2 over m. Okay, so we drew a free body diagram, wrote the force, and there you go. We could have also done it through energy considerations. We could say, well, yeah, if this is stretched by x, its potential energy is 1/2 k1 x squared. If this is compressed by x, its potential energy is 1/2 k2 x squared. So the total energy becomes 1/2 k1 plus k2 x squared. So k1 plus k2 really plays the role of the spring constant. Okay, so that was one example. So let's say this is A. Let's do another similar one here. So again, similar setup. We have a wall. Now we have two springs in series. So we have K1 here, and it's attached to another spring with spring constant K2, and then we have this mass. All right. So again, we want to find omega. So now what happens? So if I move the mass by some distance x from the equilibrium position, well, how do I know how much each spring is stretched, right? I know the sum of the length each is stretched is x, right? Because suppose, this is the natural length of this one. This is the one for this. So if this one is stretched by x1, and then this one is stretched by, so let's say this is L1, L2. From here to here, I get L1 plus x1. From here to here, I get L2 plus x2. Then, of course, here it was at L1 plus x1, so the total displacement of the mass from its original position will be x, which is x1 plus x2. So I know the sum of the length each spring is stretched as x, but how do I know what these are? Well, I can think about the free body diagram, right? And the fact that the springs are massless. So if a spring is massless, F equal ma means the net force on it must be 0, right? Because m times a is 0. So now if you think about this, the second spring K2 here, let's say there is some force on it here at the point of contact with the mass. There's another force on it at the point of contact with the other spring. Well, these two forces must be opposite direction, same magnitude. So that means the forces each of these springs applies must be the same, and that implies that K1 x1 is equal to K2 x2. Same force for both springs. Okay, so now we know what to do, right? So so let's say the force on this object is going to be again in the opposite direction, if I'm careful about the sign, is minus minus F is equal to the mass's second derivative of x with respect to time. Now I want to relate this F to x, right? So what are my equations? Well, I have k1x1 is equal to k2x2, and I have x1 plus x2 is equal to x. So for example, I can solve for x1 in terms of x2, and put it into this equation. So I get k2 over k1 times x2 plus x2 is x. And then from here, we find, if I factor out the x2, we find k2 over k1 plus 1 times x2 is x. And combining these, this becomes k1 plus k2 over k1. x2 is x. So therefore x2 is k1 over k1 plus k2 times x. We could have guessed it without doing much algebra, right? Because if the product of x and k is the same, it means x is inversely proportional to k. So that means x2 is proportional to k1, and x1 is similarly proportional to k2. Okay. Now, the first, I can write it as k2 times x2, right? So F is k2 x2. And going back here, we find minus k2 x2 is minus k1 k2 over k1 plus k2 times x is m second derivative. So again, we found the same structure, right? The second derivative of x with respect to time squared. The acceleration is minus this quantity, k1, k2, m, k1 plus k2 times x, and then we can immediately read off our omega, which is the square root of that coefficient. Notice that if I define 1 over k to be 1 over k1 plus 1 over k2, kind of like you add maybe resistors in parallel, this becomes k1 plus k2 over k1, k2. So you can think of your omega to be square root k over m, right? Because k then is k1, k2 over k1 plus k2 for this effective spring constant. So if you add two springs in series, one after the other, you can think of them having an effective spring constant given by this formula, the way that we just derived it. So the next topic I want to talk about is a physical pendulum. So instead of a mass on a string, it's really a rigid object. And then there's some pivot going through it. And again, it can perform oscillations right around that pivot point. So how do we think about it? Let's go to our notes. So physical pendulum. So there's going to be some object, there's a pivot here, there's going to be a center of mass somewhere, and then there's some distance, let's say let's see, what was it called, D or L? L to the center of mass from the pivot point, so here. So if we form an angle theta, and this object is performing rotation around that axis. So the general equation is tau is I alpha, as you remember from the previous chapter. So tau, what is tau? Well, the net torque around the pivot point, the only force that I have is the force of gravity. We can think of it acting at the center of mass. So if that length is L from here to here, this is L sine theta. So tau is mg L sine theta, and in this case it's going to be counterclockwise, so it wants to rotate it in the opposite direction as increasing theta, sorry, in this case it's clockwise, right? It wants to rotate it this way, and theta increases in a counterclockwise way. So if we say that the positive direction is counterclockwise, this is negative, so it's minus mgl sine theta. And that's I, and this is I around the pivot point, right? Around pivot, not around the center of mass. Around this point, times alpha, which is the second derivative of theta with respect to time. So small angle approximation that we used before gives sine theta approximately equal to theta. So we find minus mgl theta is I second derivative of theta with respect to time squared, with respect to time rather, and then second derivative of theta with respect to time is minus mgl over I times theta. So again, we find the same mathematical structure, and we expect our omega, the angular frequency, to be the square root of that number. For a mass on a string, right, on a massless string, which is the example we did earlier, basically around this point, I is ml squared, right? For mass on massless string. Right, all the mass is a distance L from the axis of rotation. So that works, right? The factors of m would cancel out, and then I get one L in the denominator, because the L in the numerator cancels out with one of the L's in the denominator. So we find the square root of G over L that we found before. That was a special case of this more general general physical pendulum. All right, so let's take a look at one quick question here. Yeah, take a few seconds, think about it, and then we come back and discuss it together. So yeah, so we have a solid disk, a circular loop. They have the same radius and the same mass. Okay. So they're pivoted at a point at the top, and they can oscillate there. So we want to see which one has the larger period of oscillations. So the mass is the same. They have the same radius. The center of mass for both is at the center. So the distance between the center of mass and the axis of rotation is the same. So the only thing we need to figure out to answer this question is the moment of inertia, right, around that pivot point. Which one has a larger moment of inertia? So how do I think about it? Well, if you use the parallel axis theorem, it becomes a bit more easy to understand it, right? So the moment of inertia around the pivot point is total mass times radius squared, that's the distance between the center of mass and the pivot point, plus the moment of inertia around the center of mass. So this number mr squared that gets added is the same for both. So again, the one that has a higher moment of inertia around its center of mass will have a higher moment of inertia around that pivot. And well, the ring, all the mass is a distance r away from the center of mass. For the disk, this is distributed uniformly. So some of the mass is much closer. I mean, that r is the maximum distance. So therefore, the loop must have a higher moment of inertia than the disk. And the moment of inertia was, again, it's a measure of the inertia. So it goes into the denominator for omega, which is how fast it's going to oscillate. And the period is inversely proportional to omega. So if you increase the moment of inertia, you're going to oscillate more slowly. You have a larger period. So the one that has a larger moment of inertia must have a larger period. And that's the circular loop. Right? So there were several kind of considerations, right? One is just thinking about our equation here. Again, from this I can always get my period, right? So that's this is equal to 2 pi over t. So t becomes 2 pi square root I over all of that mgl. And also physically it makes sense, right? So moment of inertia is how much inertia you have. So the larger moment of inertia, it makes sense that it slows down the oscillation. So that decreases the frequency and increases the period, the time for one full cycle. And it goes like the square root. So everything else is the same. The only thing is to figure out which one has a larger period. We have to figure out which one has a larger moment of inertia. And well, it's some of you may be able to visualize this. Think of, okay, so for the loop, most of the mass is a larger distance from this pivot point. It becomes much more easy to visualize if we think about the parallel axis theorem and say, well, the moment of inertia around this point is something that's the same for both of them, total mass times radius squared plus the moment of inertia around the center. And it's clear that for the loop, all the mass is at the maximum distance, the radius from the center. For the disk, it's distributed uniformly on the surface, so a lot of the mass is much closer, so it must have a smaller moment of inertia. I believe, if I remember correctly, it's 1/2 mr squared for a disk, whereas for the loop it's obviously just mr squared because all the mass is distance r from the center of mass. Okay, so that's a good place to stop.